Our next presenter is Connor Bolton from the University of Michigan. Connor is going to show us how we can use the sweet, soothing sounds of Katy Perry to carry out denial of service attacks on our coworkers' hard drives.
Thank you, Matt. I think Katy Perry will make a lot of us not work very properly too. So let's see what happens with hard disk drives. So sound affecting hard disk drives. That's kind of far-fetched sounding, but we've actually known about it since 2008. So in 2008, this guy put out a YouTube video where he yelled at a data center and saw massive latency spikes. And then even in 2016, there was a fire alarm drill in this bank. And when the fire alarm went off, it knocked out their data center. They attributed this to the loud sounds of the fire alarm. And this is an example of a reliability issue, right? But we really started wondering, how could this be turned into a security issue? So when we started thinking about it, we came up with two different kinds of threat models. And this is what we came up with. So the first one is using built-in speakers or built-in acoustic emitters that are already in place in the system. So that's, for example, like the fire alarms that are already in the system in the case of the bank. But it could also be something like the speakers right next to your hard drive in a laptop. The second one is using acoustic emitters that you place yourself. And that opens up many possibilities, such as using ultrasonic transducers that are the size of about your thumb and are 20 bucks, and you can't hear what they're emitting. So what this paper really looks at is how does this happen? There's two physical ways that this actually occurs on hard disk drives to prevent the hard disk drives from working properly. Then looking at how these errors propagate up through the operating system and start to affect the operating system and applications. And then finally, how could you defend against such an attack? So the first of these two ways that hard disk drives are affected is typically with audible frequencies, and that's with vibrating the read-write head and the disk platters. So on every hard disk drive, there is a read-write head trying to write data to the disk platters. And it has a target, which is the center of this thing called the track. And the hard disk drive uses a sophisticated controller algorithm to ensure that the read-write head is as close to the center of the track as possible. And as you can imagine, if you move it away from the center of the track, after a certain point, the hard disk drive does not operate properly. So that's actually on the order of nanometers, something like 10, 20 nanometers sometimes. And we did a simulation to see exactly how bad it could get. So this is a simulation in COMSOL. We looked at the displacement of the disk and the read-write head as you subject it to sound. And so we noticed that the disk and the read-write head are both displaced in vertical fashion and horizontal fashion, and it puts it outside of the normal operating bounds. That's not good for the hard disk drive. And we wanted to look at this in a real hard drive then, instead of just a simulation. So what we did was we took a hard disk drive and we used a diagnostic port and started looking at the actual position of the read-write head relative to the center of the track, so the center of its target at 0% in this graph. And the position of the read-write head, which is the blue there, needs to stay within that yellow strip in order to work properly, in this case, to write properly. On this particular drive, we didn't know exactly what the threshold is to be able to read properly from disk, but it was somewhere around here based off of other literature. It's something like 1.5 times the write threshold. So it's a little greater than the write threshold, and it's a little bit easier to read than it is to write. However, we noticed that when we subjected the drive to sound, we would make this go way outside of the operating bounds and almost outside of the track in some cases. And in this case, the drive would not be able to read or write properly. So the operating system would see this as a loss of throughput. So that we started to do throughput tests using DD properly, which would give us an accurate representation of this. And as you'd expect, as you increase amplitude, the drive stops working as well as it would normally. So this is with no sound, and then we started cranking up the amplitude a little bit. You started seeing partial losses of throughput. The drive could still write a little bit, but not as well as it could normally. Then as you further increase the amplitude, the drive just stopped being able to write at all. And this is maybe as you would expect. The worse the amplitude is, the worse the drive would perform. However, this is only one factor of this equation. So frequency actually plays a very large role in how effective the attack is. As you may or may not know, there's a property of things called resonant frequencies. And this basically will determine how much an object is affected by a signal depending upon the frequency. Certain frequencies displace them more than others. And what this means here in this graph is that as you change frequencies and change amplitudes, certain frequencies are more effective than others. And the blue here is actually where things are affected. So at that red dot there at 100 dB and about 18,000 kilohertz, or 18,000 hertz in this instance, the hard disk drive would not be able to write correctly here. So you might be wondering, what about reads? So with this specific causality, we found that reads are significantly harder to block than writes. And that goes back to this difference in thresholds. The read threshold is greater than that of the write threshold, and thus it is more difficult to block than the writes. However, this is a little bit different from the second causality. So the second causality is actually shock sensor spoofing. We found this was typically with ultrasonic frequencies. So all or most modern hard disk drives have shock sensors that are there to prevent the hard drive from having catastrophic damage if you were to, say, drop the hard disk drive. It places the read-write head in a safe position so it didn't crash into the surface of the disk. In this case, we found that you can actually use sound to alter the output of the shock sensor and make the hard drive think that it's falling when it's not, and then it parks the head and DOSes itself. So we tested this, started increasing the amplitude just like in the previous test. However, what we saw was completely normal throughput until we hit a certain turning point, and then all of a sudden we lose all throughput. And this is because this is a binary decision being made by the hard disk drive controller to park the head or not park the head, in this case park the head. It resulted in complete throughput loss. Also similarly to the other causality, frequencies plays a big role in this as well. As you can see here, different frequencies are far more effective at making the drive unable to work properly than others. One change, though, between the two causalities is that for this ultrasonic attack on the sensor, the reads are just about as easy to block as the writes, as shown in this graph. They're very similar, and that's once again because this is not actually affecting the read-write head of the disk. This is actually affecting the sensor, causing the hard disk drive to park the head when it should not be. And so we figured out these two causalities, and we wanted to see what happens next. What happens to the operating system and the applications that are using this hard disk drive? So we did some quick tests, and here is where we have an ultrasonic transducer that's underneath the laptop, and we're doing a throughput test. When we turn on the ultrasound, the throughput drops. However, what's interesting is after a few minutes, unexpectedly, the operating system just crashes. And this is something that's kind of puzzling. An operating system should not crash because of sound nearby. That just shouldn't happen. So we wanted to investigate this a little bit. And, oh, there we go. So we wanted to investigate this a little bit further. You know, how does this work in the Windows I/O stack and also in Linux? Here is Windows. So there's a couple of different kinds of ways that this error can kind of happen. This is one of those errors. So we've been talking about inducing I/O delays via sound in the hard disk drive, and that causes issues. That by itself can cause issues in applications. So one way that we did, or we showed this, is looked at video surveillance DVRs and seen how we could affect those. So we got the video surveillance DVR unmodified, just placed a speaker nearby, and blasted it with sound, see what happens. And we looked at the video after we ran this experiment. So this is the result. We started playing sound at time 0, and what's happening now is the hard disk drive, or the system cannot write to the hard disk drive. So it's saving this in its RAM until the RAM fills up in about 12 seconds, and then it just loses all the data until the sound turns off at 1:30. So essentially what happens is it's storing everything in RAM. You have it in RAM right now, and you lose that data, and then when the sound turns back off again, you write what you had in RAM and then the new data that you now have. And that's a little bit of an issue in this case. So we wanted to look a little bit further, what are some other ways that this could propagate? Because throughput delays is fun and all, but we wanted to see if there's anything more sophisticated. It turns out that in both Windows and actually in Linux too, although it's not shown, after you have a certain number of I/O delays, you can cause these timeouts in the I/O drivers. And after you have a certain number of these timeouts, it'll basically cause the operating system to not be able to communicate correctly with the hard disk drive. And what's funny about this is that even after you turn off the sound, this continues to happen. And you still can cause issues in applications this way. So this is actually on Linux. This is just a basic query to a hard disk drive. What are you is basically what this is. And the thing is, this is not even accessing data on the disk. Usually this command would fail, but in an even worse scenario, you might have something like this, where it's giving you back garbage data, which is bad. So we did not make a acoustic compression system. This drive does not actually have 2,700 petabytes of data on it. That just didn't make sense. So this is an issue. If you're trusting this data to be correct, you're going to have a problem. So we think it's this kind of communication error that causes issues in Windows 10 and causes Windows 10 to crash. Linux doesn't crash, but it still cannot communicate with the hard disk drive after this occurs. And we were able to cause this to happen even with the laptop's built-in speakers. It would essentially just load up a web page in our attack. Sound would play over JavaScript, and it would DOS the hard drive, and the system would crash. So as for defenses, we really wanted to look into defenses. The first thing we thought of was passive noise canceling, right? Just put something in between the speaker and the hard disk drive, and you'll be good. Turns out, not such a good idea. This is an early attempt. It was a bad one. Don't do this. So we eventually went with like blocks of foam and put that over in between the speaker and the hard disk drive, but it still didn't quite work right. So lower frequencies actually, to put it kind of unscientifically, bend a little bit better than higher frequency sounds. So they would actually go around the foam, we think, and affect the hard disk drive still. So you think, well, why not just encase the thing in foam? But that didn't actually work very well either, because then the hard drive doesn't operate properly because of heat issues. You could probably figure out a system that works for this, but however, you might have issues where you think this is going to cost you a lot less than it actually might. So really, this is a bad idea. We wanted to come up with something that was a little bit better idea than just this. And we started thinking a little bit, and we thought, well, maybe we could alter something like the controller. But right now, the attenuation controller in the drive, the controller just doesn't quite get things right, and things just start falling apart. It's bad. So we looked at the feedback controller, and so what this controller is doing is trying to keep that read-write head right in the center of the track when you're trying to write or read to the disk. And it looks something like this. And you have this pre-existing controller that the model and is trying its best, but it doesn't know about the attack. And that's a critical issue here. So what we did was we didn't modify the pre-existing controller. What we did was we just added a little bit of extra logic kind of almost on top of it. That's giving it essentially information about this attack. The thing about this attack is it's a little predictable. You know that you're going to try to attack the resonant frequencies of the drive, and you know your own resonant frequencies of your own drive. In addition, sound is somewhat periodic. It's kind of like a sinusoidal wave if you have a single tone. And because of that, the displacement is a little bit predictable as well. So, kind of how this works in a nutshell, you might be able to think about it this way, is that if you know you're about to be pushed left, well, then you could just move a little bit to the right so that when you're pushed, you're still in the center of the track. And that's kind of what this is doing right here. So we tested it. And so this is without the attenuation controller. That's that blue line that's going everywhere. And you can actually see in this simulation, it's actually going outside of the track itself. But it's well outside of the write thresholds and the read threshold there. However, when we added in that attenuation controller logic on top, we were able to keep it within the write threshold and the read threshold. And so what's great about this is that it seems to work properly, And on top of that, it's a firmware update. So this is completely in software. It's something that you could update to all of your hard disk drives in your data center without any extra cost besides the amount of time that it would take to design such a controller. And this would apply to legacy systems, maybe in hospitals or other applications that you can think of. So this is, we think this is a viable solution for this. There's plenty of other related work to this, and I encourage you to read it. I'm running a little short on time, so I want to get to a few questions, so I won't go through this in detail, but if you're interested in this, I really encourage you to read this. There's a lot of good work out there. So kind of in conclusion, what did we do? We looked at sound, how it can DOS hard disk drives. There's actually two different ways that this can occur. There's an audible way where it vibrates the head and the disk. There's an ultrasonic way where you manipulate the shock sensor's output and make it park the head when it really shouldn't. And then there's multiple risks there. There's you can crash operating systems with Windows 10, cause undefined behavior in other applications, and you can do this through built-in speakers and autoplay from a website. You can do this through covert ultrasonic transducers where you can't hear the sound. And finally, we kind of propose a few defenses, one of which is a hard disk drive firmware update that would protect against the vibration of the read-write head and disk. And that's that, and I'll be happy to take any questions now. Thank you.
Come on, people, don't be shy. Don't be shy. Connor's funny, he doesn't bite much. Okay, so, oh, we got somebody.
If nobody's going to do this, I'll do it. Peter Neumann again. Way back in the 1960s, there were IBM disk drives that you could actually get the disk arm to rock back and forth and tip the damn thing over. It was a really amazing experiment. But
Devin Cook, Oracle Cloud Infrastructure. So did you guys look at all at maybe somehow affecting writes or like being able to inject stuff into that? I know like the hard drives have probably a lot of error correction and stuff in there, but did you look at that at all?
So not yet. We've thought about it, and we're thinking maybe in some work after this, we might try to do something where you try to time it right, get it to write into a sector that it's not supposed to. But as of right now, we have not tried any of these tests. It's a great idea, and hopefully we can make it work sometime.
Rob Cunningham from MIT Lincoln Lab. When the ultrasonic transducer couples into the laptop itself, does it produce any sort of a thing that you as a user could feel, like if you had your hands on it?
That's a good question. I know with certain ultrasonic devices, if it's sufficiently loud enough or the amplitude's high enough, you would be able to feel it. But don't quote me on this. I think in this case you would not be able to. But actually in that test, the ultrasonic transducer was close, but it was not actually touching the laptop. So, but yeah, that's unfortunately that's all I have for that.
Okay, thank you.
Hi, Robert Lachow from MIT Lincoln Lab. So this is fascinating work. I don't know much about the area, but I understand that one of your defenses proposes like a controller. So is there hypothetically a way to fool the controller into thinking that you're attacking it so then it begins to move the head in a certain direction, but that you don't actually attack? Do you see what I mean?
I see what you mean. I think the attenuation controller works a little differently. It should work as normal, regardless of if you're attacking or not. As for trying to manipulate the controller to work against itself, I am unaware of a way that you could make that happen. Not to say that there's no way that that could happen, but as far as I'm aware, there is no way.
Okay, thank you.
Last question on the same line, since I was formerly from MIT Lincoln Laboratory. I'll gang up. So you have the controller. Is there a risk of it not detecting catastrophic events that it would have detected without your pre-filter on it?
That's a good question. So in this feedback controller, it's typically only affecting the lateral movement of the read-write head, which shouldn't be catastrophic issues. It should only be availability, being close to the center of the track. It's usually not, as far as I know, it's not really affecting the vertical positioning at all. So because of that, it shouldn't cause any extra catastrophic errors. It should only help with the positioning, I think.
Okay. Everybody, let's thank our speaker.